6.1 problems. Number one gives us specific heat of helium. That's the amount of joules it would take to push 1 gram of helium up 1 degree Celsius, which is also the change of 1 degree Kelvin. Remember that Kelvin and Celsius are the same if we're only talking about the change in number of degrees. The Kelvin thermometer is basically the Celsius thermometer with the numbers painted over. The size of the degrees is the same. A 5-degree Kelvin change is a 5-degree Celsius change. So you might see that written as Kelvin. And somewhere in here, I know that they cancel Kelvin with Celsius because they're only talking about the change, and that does work. So we know the starting temperature, the ending temperature, and it expands against a certain pressure. So the total energy will be the heat put in or out of the system and the work put in out of the system added together. So this is a very famous formula. It is on the reference page in the real test. This one is not. I went and looked. So that's why I don't recall doing it in a real test. But total energy would be the two of them added together, really. So we know the mass of the gas, we know the specific heat, we know the change in temperature. Subtract this and multiply them all out, you get joules. If the gas is expanding against a pressure, then work is going out of the system. So we're going to take the pressure that it's working against, in or out, anyway, that it's working against, and the volume that it managed to achieve, the change in volume that it managed to achieve, and we're going to put a negative on that so that if it got smaller, work went into the system. If something worked on it from the outside, then work went into the system. And so if it got smaller, that's a negative change, but we take the negative of that so that work positive went into the system. In this case, it expanded outward. It expanded outward, of course, against a pressure. So the change in volume would be a positive. However, we know that work left the system in the same way that if you fight the storm door against a spring trying to close it, then work went out of you. So with the pressure, the liters that expanded, and it turns out, I won't bore you with the details right now, that a kilopascal liter is a joule. So you can just borrow that number and convert it to joules. Then we add these up and we get the total. So if we're going to be given a bunch of heat of formations on our table, I don't know where that table is, but we'll pretend, right, that we have a heat of formation, and we can do then the sum of the products minus the sum of the reactants. However, and this is a very important point, they do think you know this, elemental states are considered to be zero. So notice it says the change in heat for the reaction. If I run this reaction one time, I need two of those, one of those, one of those, and one of those. So if I run it a mole of times, because that's what we're going to get, look, per mole, and they mean of reaction, mole of times that the reaction was run, then I'm going to form two of this. When I form water, I get negative 286. So I'm going to take negative 286, because I am forming water, right? Heat of formation of water, and I'm going to double it. This is the water. This is the nitrogen. This is the oxygen, and this is the N2H4. I only need one of these. However, I have to bust it up. It turns out that in this case, the heat of formation is a positive, but we're going to do negative of that. If you form it, you have to put energy in. Apparently, this stuff is pretty unstable. So if I bust it up, I actually get energy out. We're going to take negative of whatever they told me because I'm going to subtract out the reactants. And I'm going to multiply by the appropriate coefficient in front, in this case, a 1. Add this all up and we get that. So if this is the value for the kilojoules that you get if you run the reaction a mole of times, what would you get if you used 50 milliliters of this? Now they do give you a density. Well, if you ran it half a mole of times, you would get half that number, right? If you ran it 100 moles of times, you would get 100 times that number. So how many moles are you going to run it? Well, you're going to be limited by the fact that you have a certain number of these, don't you? So we know that with this many milliliters and this density conversion, we have a certain number of grams. At that point, we should know pretty easily how to convert that to moles. And so we have a certain number of moles. Let's say we have 70% of the moles of a mole. Then we would get 70% of this number, right? Well, it's some fraction of some sort, right? And we know that if we run the reaction one time, we needed one of those, or we needed one of those to run the reaction one time. So the number of moles of this is also the moles of the times that we run the reaction. Then we multiply by this and we get the kilojoules that would come out. Notice all the moles cancel out because we're not rating it per mole. We know exactly how many moles we're going to use. This is not an abstract figure. It's not a rating like this is. If you run it a mole of times, you will get this. This is actually what you get if you use this much. On C, we're going to do Hess's law, which is the flip and multiply method. This one is very complicated. And I just want to point out just one little example in it, really. This one is way harder than they would put on the real test. And so I'm essentially going to skip it. But just for a start, where would I start? Well, I would find something that is unique. I only see N2 in here one time. And it's a 4, and it's on the right. What do I need in the end? I need it on the right, but I need it to be a coefficient of 1. So I'm going to multiply this line by 1/4, and then I'll get 1N and 3/4 of a water. After that, this one gets so complicated that I honestly am not willing to go figure it out again. And we will have other examples of Hess's law, and I'm going to skip the rest of this one. So if this is the value that we found, it's a negative. So does it take more energy to break the bonds of the reactants or those of the products? Well, if energy came out to run this toward the products, then the products are more stable. So if energy came out of this, that's because nature took the opportunity, given the materials and situation at hand, to release as much energy as possible, and this is what it came up with. So those products are the most stable, least energetic things, most chaotic things it could find. So which is more stable? The products, because if energy is coming out, it's creating something more stable. That's why I did it. It created something less energetic, more chaotic, with the atoms spread out in a wider way through the universe, and more stable than it started with. So the products are more stable. It would take more energy to break these bonds than those bonds. In 6.1 lesson, we have an example of something very similar where they dissolve NaOH in water. So this is kind of a repeat concept. What you have to do, though, is take this solid and bust it up. Now, this must be some version of stable. Otherwise, why is it still this way? Everything that you come across is some version of stable. Otherwise, it would have already come apart or exploded or something. Plus, we know that table salt is pretty solid. If you don't put it in water and you keep it dry, it'll just last, I don't know, 1,000,000 years or something, right? So you do have to put in some energy to bust it apart. Not a lot, I admit, but we have to put in some energy to break it apart. So you have to put in some amount of energy to break it apart. And we go and look at the table somewhere, or it's given in the problem, and we know that we're going to have to bust this up. So it's going to be a positive of the lattice energy, the solid breaking or forming energy. We're going to break it up so energy goes in. Now, this is interesting. You have to get water to stop being so attracted to itself so that it can turn and interact with this. And just for a moment, it's independent. This water molecule that I broke apart from its liquid neighbors where it was attracted is independent. And in that sense, it's a gas. It's not actually a gas, but it is acting independently. And I don't have an independent indicator, so we will call it a gas. It is, in some sense, actually a gas just for a moment. Now I have to break it apart from being attracted to its neighbor, so I have to put energy in, and I would have to be given this value. Enthalpy is heat. It's vaporization because I'm turning it somewhat into a gas. And in this case, hydration, meaning we're going to settle these in so that they stick to water in some sense. Now I've got these broken apart, and they're going to settle into water. Now, The fact that they're settling into water once again means that this is nature's choice for releasing as much energy as it can given the circumstances, or maybe also creating as much chaos as it can create considering the circumstances. So what ends up happening is a version of this, where the plus ions are settled in and attract the negative side of water. The negative ions settle in and attract the positive side of water. And that very much could be a multiple choice question or even a free response on the real test. So the settling in nature is an energy release. That's why nature did it. So we're going to take the amount that we were given, call it negative. The same thing here. So we're going to take these and add them up and get the overall kilojoules per mole. Now on B, interestingly, they say that this was a little too theoretical, and when you do it for real, you actually get this number. Okay, so what's the final temperature if you use 100 grams? Again, this is if you use a mole of it, right? So we're not going to use a mole, we're going to use 100 grams. This tells me how many moles I'm going to actually use. And so then I'll use a certain percentage of this, correct? This will essentially be a percentage. This will multiply times the rating per mole, and this will give me how much I'll actually use. Now, this was a positive value for the rating on dissolving the salt. If energy went into positive value, the process of dissolving, then where did it get that energy? Well, it got it from the only source at hand, and for that, it was the water. So the effect on the water will be negative of whatever you just said. If energy goes into this process, then it went out of the water. The water was the source of the energy. And vice versa if the process was negative. So the effect on the water will be negative of whatever you just said about the reaction. So we're going to take this number and call it negative of that. And we know that Q for reaction is equal to MC delta T. Now, let's convert this to joules so that it cancels with this joules. If you don't do that, your answer is off by a factor of 1,000. We also know that 1 gram of water is 1 milliliter of water. 1 milliliter of water weighs 1 gram. And they think you know that, or at least it's very, very, very handy. Now, for my favorite people, all you super nerds out there, to be extremely picky, that's only true at a low temperature, something like 4 degrees Celsius, but it is close enough for most engineering purposes and close enough for this test. Because they have so much to talk about, they cheat a little bit and just call water and even many solutions with stuff dissolved in it as 1 gram per milliliter. So if you have 100 milliliters, you have 100 grams of water. This is the specific heat of water because it is a fact, and they will tell you that. And personally, I would have just solved for delta T. So if you run this and solve for just delta T, you get this. Delta T is 15.84 degrees Celsius, or the change in temperature. Now, we also know that energy was going out of the system, so the temperature must be going down. It must be decreasing from this, so I could perform this and get the temperature at the end. A bomb calorimeter is just a container in which you burn stuff to find out the heat evolved. And in this case, as far as I know, bomb just means container. So we're going to do this in a self-contained container, in which case we don't need grams. We're going to run enough experiments on this container, this system, that we know how many joules it takes to increase 1 degree Kelvin. And the capacity, the materials, the mass of the container are all factored in intrinsically by doing experiments on the real item. So I don't need mass for the container. I just need joules for the container to push it up 1 degree Kelvin. This is also the case where I mentioned where they cancel K Kelvin with Celsius, but that does work because we're only talking about the change. And a 5 degree, for instance, change in Kelvin would be a 5 degree change in Celsius. So that does work. So we know the change in temperature. We know it went up because we were burning cereal in there. So we need a positive number. Multiply and we get the joules that come out. So As far as the system outside the process of burning is concerned, it's a positive value. If you're going to burn this, heat goes outward into the rest of the system, right? Out of the cereal into the rest of the container and water and all this stuff that you've got. So that would be a positive. So we're going to subtract this so we get a positive, and when we multiply, we get a positive number. Outside of the cereal, energy has been gained. So what is the rating for the cereal? Well, we know that energy came out of the cereal, right? It is the negative of whatever we got here. If this is a positive, it's because the cereal supplied it. That means that the cereal is a negative value. Energy left the process of the burning of the cereal. The cereal atoms now have less energy than when they started. They have a negative change. So we're going to borrow this number, turn it negative, and then convert it to calories. So small c calorie, and that is very important, small c, is the energy for water to go up 1 degree C per gram. And that's its definition. You know how much energy it would take to push 1 gram of water up 1 degree Celsius? We're going to call that a calorie. Now, I said it was a small c, and capital C, calorie, which you're used to from your food packets, if you live in the United States at least, is 1,000 small c calories. So this is sort of a chem lab calorie, and a nutritionist calorie is 1,000 of those. Because a human sort of average maybe diet consists of 2 million small c calories a day, and that got annoying and a little unwieldy. So nutritionists and the American FDA deal in kilo calories, or capital C calories. So this is also 4.18 joules, isn't it? The energy it takes to push 1 gram of water up 1 degree Celsius is 4.18 joules. So 1 calorie is 4.18 joules, or 1,000 calories would be 1,000 times as much. And that's why this conversion works here. And we get capital C calories. So number 5, we want to target the rating for the neutralization of this strong base and strong acid. And we're going to get kilojoules per mole, and that's mole of reaction, or it's mole of these used. It's kind of the same thing, because if you use one of these and one of those, you get the reaction run 1 mole of times. So it just kind of depends on which way you view it in this case. We know that Q equals MC delta T, and they told me milliliters of solution and told me to assume that it's close enough to 1 gram per milliliter as to make no difference. So this will give me grams of solution, or water, essentially. This is the specific heat of water. This gives me the joules then it would take to run this much water up this change. We know the temperature went up, so we get a positive value in joules for the change in water. So if the energy went into the water, where did it come from? It came out of the process of the reaction. So again, that's the negative of whatever we just said. If energy went in, then as for the reaction, that value is a negative, isn't it? So we're going to borrow this number, but remember we have a negative sign on it now. And what we want to do is divide by the moles. So we're going to go and take liters times molarity, which gives us moles. They said HCl. Honestly, they could have done the same thing for NaOH. It doesn't matter which one, really. What you really need is the limiting reactant, honestly, because that would be the thing that governs how many times this reaction can run. In this case, they designed it so that they run out perfectly together, so it doesn't matter which one. In a sense, they are both the limiting reactant. This gives me moles of reactant, or also the moles of times that the reaction runs, same thing in this case. And we get joules per mole, and we know that it's a negative because we know energy was released. Otherwise, why did the temperature of the solution go up? And it's often stated in kilojoules per mole. It's just a handier number. And so they also converted it there. Here we want to talk about the combustion of ethanol. That's the drinking alcohol, the beer, wine, spirits alcohol. And of course, it does catch on fire if you get it strong enough. It's the source of many of those exotic flaming desserts and so forth. If you get the alcohol strong enough in water, it'll burn. And of course, pure, it burns like crazy. And this is octane, which you see rated on your gas pumps. So you bet it burns. So we're going to write out the balanced equation. I'm going to assume you can do that. Notice they used a half here. You could, of course, just multiply this whole thing by 2, but then you have to multiply this by 2. Okay, so you can get the right answer that way, but it said 1 mole and 1 mole, so we need to use the half so that we use 1 mole. Also, we know that combustion always releases energy. It's always exothermic, so these are negative. Even if they don't say it's negative, it actually is negative. Well, which releases more energy per gram? So we're going to convert the moles on the bottom to grams on the bottom and divide then. And it turns out that octane releases a good bit more kilojoules per gram. So if you're flying a plane, you would rather run octane than alcohol. They don't actually use octane. Now, if you were going to convert the ethanol into octane, you would also generate some oxygen and water. And here's our balanced reaction for that conversion. And so it is possible to flip and multiply, do Hess's law on these two to generate this. So what I want to do is find something that's unique. Now, that's not very hard on this one. The ethanol only exists in one place. It's not anywhere else in these two reactions. So I can pin it down and be very certain of myself. It's on the left side. Well, in this case, it's on the left side. That's great. But this is an 8 and that's a 1. So I'll multiply this whole thing by 8. I'll multiply it by 8, which means I also must multiply its delta H by 8. Multiply this by 8 and get this. Then the octane is on the left. And it's a 1 when I need it to be on the right and be a 2. So I'm going to have to multiply this whole thing by 2 and flip it end to end. And I get this. That means I need the negative of the delta H value multiplied by 2. Remember, I did it twice and I did it in reverse, which reverses the energy negative of and doubles it. And then I can add this up. Now, as I recall, you wouldn't be asked to sketch this, but you might be asked to interpret it, certainly. And they're telling you flat out, this bond is longer than that one, which is longer than that one. So on the internuclear separation, the distance between the center of the nuclei in these bonds, this one will be farther apart, a greater separation than this one, which will be greater than this one, because this is less separation and more separation. Now, the bond energy thing gets complicated. When they say that this is lesser than that, what they mean is if you're going to form this, you get out less energy. If you're going to break it up, you have to put in less energy. So let's review this from the point of view of forming it. If you form this, you get out less energy. So it releases less energy, which means it has more potential energy left to do work, more than the others. If you want to break it up, you have to dig out of a smaller hole. You have to pump in less energy to get back to where you can do something with it to break this, and you have to break this up. You have to put in less energy to break this up. It has more potential energy. You don't have to do as much to get it to the point where it is able to do work by separating the atoms. So this has a smaller hole to dig out of than this one, which is smaller than this one. This one released more energy. It has a bigger bond energy. When you form it, you release more energy, which means it has less potential energy left. And you have to put in more energy to break it up.